Hello gems! Welcome to another video of ACE series. The topic that we are going to discuss today is mechanical properties of fluid. The chapter that we had kept on hold for a long time. Yes, we are going to discuss it today. Just one thing before I begin, I just want to say that don't wait for things to get perfect. Okay, things will never get perfect. Start with whatever you have, start wherever you are. If you wait for things to get perfect, you'll end up with nothing. Okay, so with that thought, let's begin today's class. So alright, here we have question 1 and 2 from the SE category, the super easy category. Okay, so question 1 from 2011, viscosity is the property of liquid due to which it. Okay, so you have to select an option among this which is an effect of viscosity. Select an option which is an effect of viscosity. Okay, so I can refer to viscosity in a plain simple manner as friction in liquid. Okay, I can call viscosity to be simply as friction in liquid, right? So just like friction in solid used to oppose relative motion between any two relatively moving object, here also viscosity will oppose relative motion. It will oppose relative motion between the layers. Okay, if you know there is relative motion between the layers of the liquid, okay, layers of the moving liquid, there is relative motion between them because their different layers move with different velocities. Okay, so there is relative motion and viscosity is going to oppose that relative motion. So option B is the correct choice. Okay, viscosity opposes relative motion between the layers of a moving liquid. Okay, and if you see option A is an effect of surface tension, option C is also an effect of surface tension, and option D is something very random. Okay, let's come to question 2 now. The lift of plane is explained by. This was asked in 2007. First of all, option C and option D out of the choice. We are discussing fluid today. Big brains? No, small brains, because during exams, of course, you won't have chapter wise questions, right? The questions will be in haphazard manner. Okay, so anyways, you should not learn physics in parts. Okay, learn it as a whole. One question can be easily mixed with some other question. Okay, so learn physics as a whole, not in part. Anyways, let's come to this question. So we have to explain the lift of the plane. So in this, we'll consider a plane over here. Now, due to its shape, the plane will cut the air into two parts, one in the upper region, okay, and one in the downward region. Okay, the air in the upper region usually has a higher velocity. Okay, the air above the plane in the upper region has higher velocity and air below the plane has lower velocity. Now, applying Bernoulli's principle, you can state that, you can see that the upper region will be an area of low pressure, right? High velocity means low pressure. This is applying Bernoulli's principle. Okay, there is the velocity of air in the upper region is high, so the pressure over here is low, and here the velocity is low, so the pressure is high. Okay, using Bernoulli's principle, so you can see that the plane will be pushed from the region of high pressure into the region of low pressure. Okay, the plane will be pushed by this high pressure into the region of low pressure. Okay, so what did we use to explain this? We explained this using Bernoulli's principle. Option B. Anyways, the answer is from fluids. Okay, so let's move to the next set of questions now. Question 3 from 2005. This time, in this question, capillarity causes rise in liquid in a tube if theta, the angle of contact, is acute, obtuse, 0 or 90 degree. Okay, so some of you might directly know it as a result that if a liquid forms acute angle of contact, there will be rise in the level of liquid in the capillarity tube, right? And if the angle is obtuse, there will be fall or depression in the liquid level in the capillarity tube. I repeat it. Acute angle says there will be rise in the liquid in the capillarity tube. Obtuse angle says there will be fall or depression in the liquid level in the capillarity tube. Since in this question we want a rise, the option will be acute, right? The angle of contact should be acute in order to have a rise in the liquid level. Anyways, I'll go ahead and explain why is it so. If you already know the explanation, you can skip over to the next question, or anyways you can listen to it just one more time, just like Spotify ad. Okay, so I'll explain it in two ways. One is the conceptual way that will tell you how and why it happens, and second way is the formula way. Anyways, let's dive into it. So here we'll have a liquid. Okay, then we'll have our capillarity tube. Okay, Now we'll assume that liquid forms acute angle of contact. Okay, we'll say what happens when it forms acute angle of contact over here. So you should remember, for acute angle of contact, the meniscus is concave. Okay, remember this. For acute angle of contact, the meniscus is concave, and for obtuse angle of contact, the meniscus is convex. Okay, so for acute angle of contact, the meniscus is concave. Okay, concave over here. Now you can see that this is exposed to atmosphere, so the pressure over here will be P naught, the pressure over here will be P naught, right? And the pressure in the capillarity also, since it's open from the upper end, the pressure over here will be also P naught. Okay, but just if I come just below the meniscus, in this level, this horizontal level of the fluid, okay, you can see that the pressure will decrease. Why will the pressure decrease? You might have learned this in the subtopic of excess pressure in liquid drop. Okay, you might have learned that the pressure on the concave side is more. It's more by 2T by R. Anyways, let's not go into the value. So pressure on the concave side is more. Pressure on the other side will be a little less. Okay, so its pressure over here is somewhat less than P naught. Okay, so pressure over here is less than P naught. Suppose the pressure is X over here, so the pressure over here is less than P naught. So what will happen, since the pressure wants to be equal at the horizontal level, since the pressure is same throughout the horizontal level, what will happen is that the liquid from here and the liquid from here will flow into the capillarity. Okay, the liquid from both the sides will flow into the capillarity, hence there will be a rise in the liquid level. Okay, and the flow will be such that this depression in pressure, whatever less, now the by value, if you see the amount of pressure it's lacking is 2T by R, right? This much amount of pressure is less over here. Okay, the pressure over here, if you want to know the value of this X, it is P naught minus 2T by R. Okay, so the pressure it is lacking is 2T by R, right? So what will happen, the liquid will rise in this column. Okay, liquid will rise in this column in such a way that the pressure due to this column, pressure due to this liquid column, which is rho GH, will be equal to 2T by R. Okay, so for acute angle of contact, you can easily see that there will be an rise in the liquid level. Okay, there will be a rise in the liquid level in the tube. You can prove it for obtuse too. You can prove that for obtuse angle of contact, it will form convex meniscus. Okay, so for it will be just the opposite case. You can prove that there will be fall or depression in the case of obtuse. Okay, let's prove it by the formula now. So what is the formula for height of this liquid column? You might know it by heart. H is equal to 2T cos theta by R rho G. Okay, H is equal to 2T cos theta by R rho G. Now you can see that we want rise, right? We want rise in the liquid level. So this H should be positive. For rise, H is positive. For depression, H is negative. Okay, since we want rise, H is positive. So if you see, this is constant, all of these are constant. Okay, these are positive constants over here, T, R, rho, G. Only thing that H depends on is cos theta, right? The angle of contact is varying over here. Okay, so H depends on cos theta. So since we want rise, since we want H to be positive, this cos theta should be positive. Okay, and when is cos theta positive? Cos theta is positive if the angle is acute. Okay, if cos theta lies in the first quadrant, the value of this H will be positive. Cos theta will be positive and this value will be positive. Okay, and that is exactly what we want. So anyways, in whatever way you want to know it, either you can by heart the result, acute rise in the liquid, obtuse fall in the liquid level, or you can see it through the formula, you can see it through the concept as well. Okay, I'll recommend that you should by heart the result. Anyways, we took a long time for a super easy question. Over to the next question. Question 4 and 5 over here. In question 4 from 2018, you are given a container filled with liquid. You have immersed a capillarity tube in that container. That capillarity tube is itself attached to a horizontal pipe. Okay, now air is blown through that horizontal pipe. You are supposed to comment what will happen to the capillarity rise in this case. Will it increase? Will it decrease? Will it remain same? Or will it become 0? Okay, so let's think about it. Now you can see that when air is blown in this horizontal pipe, the velocity of the air molecules or the velocity in that region will increase, right? So the velocity of the air molecules in that region is more as compared to the velocity of the air molecules in this region, right? So velocity over here is less, okay? Velocity in the capillarity, okay, just above the liquid, you can see that velocity of the air molecules over here in the capillarity is less as compared to the velocity in the horizontal pipe where air is blown, okay? So the velocity over here is more, okay? So by applying Bernoulli's principle, you can see that the radius form you can apply, and you can see that where there is high velocity, there the pressure will be less, right? High velocity means less pressure, okay? Bernoulli's principle. Now here, since the velocity is low, velocity of the air molecules in this region is low, so you can say that the pressure will be more over here, okay? Now it is very clear that your liquid will flow from the region of high pressure to a region of low pressure, or you can also say that the liquid will be sucked into the region of low pressure. Okay, since the liquid moves from a region of high pressure to low pressure, there will be a rise in the capillarity. Okay, so you can see that the capillarity rise will increase. Okay, the rise in the liquid level will increase. Actually, this is what happens in your deodorants. Okay, whenever you press the knob, you actually create a region of low pressure over there. So the liquid in the bottle gets sucked up into the low pressure region and it is sprinkled out. Okay, now you have a nice way of comparing it. Okay, you can compare this system with your deodorant. Now in question 5, you are given a weirdly shaped container. Now you are supposed to find the pressure at point P. Okay, find the pressure at point P. Now this is a very simple question. Actually they have just tried to make it seem complicated, but it is in fact very simple. Okay, so the pressure at point P will be simply given as rho gh, or let me write it as rho gx. Okay, where x is nothing but the depth. Okay, the takeaway point from this question is that the pressure does not depend on the shape of the container, right? Pressure over here will not depend on the shape, right? It will just depend on the depth over here. Like they just have tried to make you confused that you'll consider the cost factor and all, but remember that pressure does not depend on the shape, right? So you have to just look out for the depth. So you can see that the depth will be from the mouth of the container till point P. Okay, so let us call this x. Okay, so the pressure over at point P will be rho gx, right? Rho gx. So what is that x? You can see simply that it is nothing but h minus h, right? H minus h will give you x. Capital H minus small h will give you x. So the pressure is h minus h into rho g. H minus h into rho g. Option C is the correct choice. Let's move to the next question now. So question 5 over here, in this question we have a container filled with liquid which has a viscosity eta subscript L, and you have an oil droplet at the bottom of this container which has the oil has viscosity of eta subscript O. Okay, now this oil drop will rise in that liquid. You are supposed to find on what factor will the velocity of the oil droplet depend. Now it is very clear from the question. We can see it in terms of force first. Okay, so we can see that the force on that drop will be only due to the viscous force of the liquid, right? Due to the viscosity of oil, the droplet will not put some force on itself. Okay, due to its own viscosity, of course it will not put any force on itself. I mean to say the only force on that drop will be due to the viscosity of the liquid. Okay, so there will be change in the velocity of the liquid due to the viscous force or the viscosity of the liquid only. So the velocity of the drop will depend on the viscosity of liquid only and not both. Okay, keep this question in mind. Let's move to the easy category now. Okay, let's step up the level now. Let's move to the easy questions now. Question 7 on your computer screen now. So it is from the easy category. In this question, you can see that you have a pipe of non-uniform cross section. The velocity, now water is flowing in this pipe. So velocity at a point X is given as 10 meters per second. Area of cross section at that point is 2 centimeters square. You are supposed to find the velocity of the water at a point Y. Okay, at a point Y where the area of cross section is 25 millimeters square. Very simple question, formula based question, right? What will we use? Equation of continuity, which says a1 v1 is equal to a2 v2, or here in our case we can say vx ax is equal to vy ay. Now the only one thing that you have to be careful about is the units. Okay, you can see different units over here. We want the answers in meters per second, so be careful about the units. Okay, so vx is 10 meters per second. Ax will keep it in centimeters square, 2 centimeters square, and we'll convert this ay. Now we want vy, so let's bring this ay over here. We'll convert this ay in centimeters second square. Okay, so 1 millimeter is 10 to the power minus 1 centimeter, right? So square this, since it is millimeter square, so 25 into 10 to the power minus 2 centimeter square. Okay, so this centimeter square and that will get cancelled, so we'll have 25 into 10 to the power minus 2. Okay, so we can take it on top, so it will be 100 over there and divide by 25. 25 fours are 100 and 2 fours are 8, 8 tens are 80. So 80, option C, 80 meters per second, right? 80 meters per second is the correct answer. Over to the next question. Question 8 over here. In this question, a spherical ball is dropped in a liquid column. You are supposed to guess the correct V versus T graph. Okay, this question will be a cakewalk for those who know the concept of terminal velocity and Stokes' law very well. Okay, so first of all, you can see that when a spherical ball is dropped in that liquid, the velocity will go on increasing. Am I right? Yes, the velocity will go on increasing due to acceleration due to gravity. Okay, so velocity will go on increasing until the weight is balanced. The mg in the downward direction is balanced by the upthrust by the liquid and the viscous force by the liquid. Okay, the velocity will go on increasing until the net force becomes 0. And when will be the net force 0? It will be 0 when the weight, which is in the downward direction, is balanced by your upthrust, okay, and your viscous force. Okay, so first of all, velocity should increase and then it should attain a stable value. Okay, so it should attain a fixed value, which is terminal velocity. Okay, actually you could have just compared this with a raindrop. Okay, raindrop falling from earth, and the fluid in that case would be air, right? Air would be the fluid and liquid drop will be the spherical ball over here, right? So you could have just compared it with that. So what I said, velocity should first increase, it should go on increasing and then attain a fixed value. Okay, so option B is the correct choice over here. Velocity goes on increasing and then attains a fixed stable value, which is the terminal velocity. Here you can see that velocity of course won't go on increasing. There is viscous force which is finally which is going to balance the weight. There is a viscous force and upthrust which is going to balance the weight, right? So velocity will attain a fixed value after some time. Of course, velocity is not decreasing. First of all, it is increasing due to acceleration due to gravity. And here also, this graph, what's happening, velocity is decreasing, right? So velocity is of course not decreasing. So option B is the correct choice. Let's move to the next question now. So question 9 over here, in this question you are supposed to find the work done in blowing a soap bubble from an initial radius of 2 centimeter to a final radius of 5 centimeter. Okay, so surface tension of your soap solution is also given. Now the approach is very straightforward, right? The work done in this process will be nothing but the change in surface energy, right? So the change in surface energy here will be given as T into delta A. Is this correct? Tell me down in the comment section if this is correct. Mention whatever time it is and say yes or no. Okay, yes, this is correct, or no, this is not correct. Don't wait for the answer. I'm going to answer it in 3, 2, 1. This is not correct. Okay, because here we are talking of soap bubble. For soap there are two free surfaces. Okay, for soap bubble there are two free surfaces which of course we cannot see by naked eyes, so you have to multiply this by 2, okay, in order to account for those two surfaces, two free surfaces. Okay, so 2 into T into delta A is the correct formula for a soap bubble. For liquid bubble it's simply T into delta A. Okay, anyways, let's solve it now. Now it is just calculative over here. Okay, nothing much more. 6, T is 6 into 10 to the power minus 2. Change in area, final area minus initial area. Now soap bubble will be a sphere, so 4 pi r final square minus r initial square, right? I just took the 4 pi common, so 2 6 are 12 into 10 to the power minus 2. 4 into pi is around 12.56 into this is r final square, 5 square. Now this is in centimeter, right? Let's convert that into meter by multiplying it by 10 to the power minus 4. I took 10 to the power minus 4 common from both. Okay, so now 5 square 25, 25 minus 4 21. Okay, 21 over here, and here you'll have 12 into 12 which is 140. 12 into around 12, so it will be something between 144 and 169. Okay, this number will be something between 144 and 121 into 21 into 10 to the power minus 6. Okay, so let's consider this as 160. So 16 into 21, that will give us, I'm just approximating, okay, the answers are a bit far away. So yeah, so 16 twos are 32, 6, and here you'll have 3 and 3. So 336, this will be around 336, and this was 160, right? So 336360, and we have into 10 to the power minus 6. So we can move 3 decimals, 1 2 3, 3.36 into 10 to the power minus 3. So around this. Okay, so we made some approximations, that's why we are getting 3.36. So option B is the correct choice. Let's move to the next question now. Okay, question 10 over here. In this question you are given an ocean of depth 2700 meter. First of all, who measured it? The math guy who buys 60 melons for no reasons. Okay, that guy measured it. So depth of ocean is 2700 meter. You are also given the compressibility of a certain material. Okay, this value. You are supposed to find the fractional change in volume when a sphere of this, okay, when the sphere of this material is taken from the surface to the bottom of the ocean. Okay, so I hope the question is clear. First of all, you should know what is compressibility. Okay, what does this term compressibility means? Okay, so compressibility is nothing but the reciprocal of bulk modulus. Aha, elasticity. Okay, so compressibility, if you didn't knew it earlier, note it down somewhere that compressibility is the reciprocal of bulk modulus. Okay, and how is bulk modulus given? Bulk modulus is given as P by delta V by V, right? P by delta V by V. So here we want the reciprocal, just substitute the value of bulk modulus over there. So we'll say delta V by V by P, right? Reciprocal. Okay, delta V by V by P. Okay, so since now we want the fractional change in volume. Okay, this was worded in the question, so you should know that what does this mean. This means fractional change in volume. Okay, so delta V by V, since we want delta V by V, we'll take that P to the other side. That will give us Kp equals delta V by V. Okay, so just plug in the values over here. P will be the pressure, which will be rho gh, right? Rho, the density, here it is ocean, right? So density of water, of course. So density of water, g acceleration due to gravity, and g is the depth, h is the depth, sorry. Okay, so K into P. K is 45.4 into 10 to the power minus 11 into rho gh. Rho, actually you should know the density of water by heart, which is 10 to the power 3 kg per meter cube. Okay, it is 10 to the power 3 kg per meter cube. So rho g, acceleration due to gravity, will take it as 10 into h. Into h, depth is 2700. Okay, so 1 2 3 4. Okay, 1 2 3 and again 3, so that is 6. So 45.4 into 27 into this will be 10 to the power minus 5, right? This there are 6 zeros over here, so 10 to the power 6 into 10 to the power minus 11, that will give us this answer into 10 to the power minus 5. Okay, so we'll solve for this. Where can we solve? Here, 45.4 into 27. Okay, 7 4 are 28, carry 2, 7 5 35, 36, 37, carry 3 7, 4s are 28, 31 plus this 2s are 45, 2s are 90, 90.8, I think. Yeah, so 908 maybe, right? So 8, 8 at 16, but this will be 15, and here 2 and 12. 12258. Okay, that will be the answer. I hope I didn't do any calculation error. So here shift to decimal, so 122.58 and into 10 to the power minus 5, right? 122.58 into 10 to the power minus 5. Again shift to decimals. So I think I made an error over here. It should be 122.58. Okay, just one decimal shift. This is not a point. Okay, so here we'll get 122.58 and 3 decimal shifts, which means it will be 1.2 into 10 to the power minus 2. Okay, now you can approximate it to this one. So option B is the correct choice. Let's move to the next question. I hope this approach is very clear. Okay, please note this down, that compressibility is nothing but reciprocal of bulk modulus. Over to the next question. So question 11 over here. Now note that the level has increased. Okay, it is from the easy moderate category now. So pull up your socks. Let's do this one. So in this question you have a capillarity tube. Initially you have a capillarity tube of radius r. You note that the mass of this liquid column, okay, mass of this liquid column is capital M. Now you take a capillarity tube of radius 2r, okay, twice the radius. Now you know that the mass of this liquid column is M dash. What you are supposed to do, you are supposed to express this M dash in terms of M, okay, or find this M dash in terms of M, okay, find this M dash in terms of M. So first of all, in the first case we can write as mass equals density into volume. Okay, you can pause and try this one. So mass equals density into volume. In both the cases you can see that we have not changed the liquid. The only thing that we have changed is the capillarity. Okay, here of radius r, here of radius 2r. So density will not change, right? Since we have not changed the liquid, the density will not change in both the cases. Okay, so mass in this case it is capital M. Density, let's take it rho. Okay, density of this is rho, this will be also rho. Okay, and volume we can write it as area into height, right? We can write volume as area into height. Area will be the area of cross section of this capillarity, and height will be the height of this liquid column, right? And that is nothing but rise in the capillarity. Okay, so you can see composition of concepts over here. So area of cross section is pi r square, right? Radius is r, so area of cross section is pi r square, and here h will be something. Okay, let's consider this as k. We'll consider this as k. First of all, let's write the formula for h, the rise in capillarity. H is nothing but this height, right? This height is nothing but the rise in capillarity. So let's write the formula for it. H is 2t cos theta by r rho g. Okay, 2t cos theta by r rho g. You can see that h is inversely proportional to r. Okay, h is inversely proportional to r. We will come to that. So now in this case, in the second case, we'll again apply mass is equal to density into volume. So m dash, which is the mass in this case, m dash is equal to density. Density is the same, right? Density is rho into volume. Volume we can write it as area into height again. Now the height will be different, right? Because the height is inversely proportional to radius. Height is inversely proportional to radius, and radius has changed. Okay, so let's write it as h dash, and this area will write it as a dash, because radius has changed, area will of course change. Okay, so here we'll have pi r into 2r square, which will be 4 pi r square, right? Just squared that 2, so 2r square, which is 4r square. Okay, and into h dash. Now what will be h dash? You can see that h is inversely proportional to r. So when you increase the radius to 2, when you increase the radius by 2, multiply the radius by 2, the height will get halved, right? I hope you are getting my point. The height is inversely proportional to the radius of the capillarity. So when you make the radius twice, the height will become half. Okay, so height will become half of the initial height. Okay, this will be h by 2. Let's consider this as m only. Okay, this is m, right? M is pi r square into h. Okay, so here this and this will get cancelled, and we can write it as 2 into pi r square 2 into pi r square rho pi r square into h. Okay, so here you can see that this is nothing but m, right? This is nothing but equal to m, so m dash is nothing but twice into m. Okay, m dash is 2 times of m. Okay, this was a matter of coincidence. Don't take it this way that when you increase the radius 2 times, the mass in the capillarity will also increase by 2 times. No, this was a matter of coincidence. Okay, it is coincidence that you increased it by 2, the radius by 2, the mass also doubled. Okay, this was a coincidence. Okay, anyways, the answer is 2m. Over to the next question. Question 12 over here. In this question, you have a liquid. The velocity of different layers of this liquid is given by this equation. You are supposed to find the stress at y is equal to a. Y is the vertical distance, or more properly, you can refer to y as depth. Okay. So first of all, you can pause and try it. So you can see that the force between the layers, is given as eta a dv by dz, right? In place of z, we have y in our case, right? Y is the vertical distance or depth in our case, so I can write it as eta a dv by dy. Okay, since we want to find stress is nothing but force per unit area, right? So force by area will give us the stress at a particular point, and that will be eta into dv by dz. Okay, let's consider the viscosity of this liquid to be eta. It's also given in the options, you can see that. Okay, so all we have to do is, now this is dv by dy. Okay, I justified it because y is the depth over here. Okay, so dv by dy. Okay, so all we have to do over here is just find this dv by dy and then plug in y equals a. Okay, find dv by dy, then plug y equals a. So first of all, let's find dv by dy. Okay, so k is a constant, 2y square. So y square, that will give us 2y, and 2 into 2, 4y. Okay, so 2y square has a differentiation of 2y. Okay, so that will give us 4y by a square, minus here 3y square, y cube will be 3y square divided by a cube is a constant. Okay, so now substitute y is equal to a. Okay, just substitute the value y is equal to a. So you will get 4a by a square, so that will give you 4 by a, right? 4a by a square, so 1a will get cancelled, and here you will get 3a square by a cube, that will again give you 3 by a. Okay, it will be 3 by a this time. Okay, so you can see that it will be dv by dy will be k by a. Take this a common, 4 minus 3 is 1. Okay, so dv by dy at y is equal to a, dv by dy at y is equal to a is k by a. So this will give you the stress at y is equal to a. The stress at y is equal to a is eta and dv by dy, which is k by a. Okay, so the stress at y is equal to a is eta k by a. Eta k by a. Okay, I hope that is clear. You could have done this by another approach as well. You can see they are messing up with the terms up and down, so you could apply dimensional analysis as well. Okay, this question could be done in that way too. Anyways, this was the conceptual way of doing it. Anyways, over to the next question. So question 13 over here, I don't know what has happened to the markers. The one which was purchased recently has run out, and the one which was assumed to be not working is hopefully working. Okay, so in this question we have a balance. On that balance, on one hand you have metal A, on the other hand you have metal B. Okay, you are given the following data: metal A, the mass of metal A, the density of metal A, the density of metal B. You are supposed to find the mass of metal B. It is given that when you immerse this system, when you immerse that balance in water, okay, they occupy the same level, which means that the balance is balanced. Okay, what a language. Okay, so when you immerse this, they occupy the same level, which means the balance is balanced. Okay, you have to read between the lines now what is meant by the balance is balanced. Okay, you can pause and try. So the balance is balanced simply means that the weight of metal A equals weight of metal B. No, it means that apparent weight of metal A equals apparent weight of metal B, because the balance is balanced in water. Okay, so apparent weight, the concept is apparent weight of metal A. So apparent weight of A equals apparent weight of B. Okay, so here we can write MA into G minus upthrust on metal A. Okay, this is the apparent weight, right? The force in the downward direction mg minus the upthrust will be the apparent weight, will be equal to mbg, which is the weight of the metal B, minus the upthrust on B, that will give us the apparent weight of B. So MA is 32, acceleration due to gravity, and now we'll keep it as G. You can see that upthrust will be, now this is entirely immersed, okay, entirely immersed. So you can see that upthrust on A will be volume of it, volume of the solid, density of the liquid, okay, density of the liquid, density of the fluid, okay, or density of the liquid only will take water, no? So into G, right, V rho G, upthrust is V rho G, volume immersed, density of the liquid into G, okay, and here we'll get MBG, MB, the mass of B, not given, we are supposed to find it, into G minus, this is volume of A, right, volume of A, here it will be volume of B into density of your water again and into G. Okay, upthrust is given as volume immersed of the solid into density of the fluid or the liquid into G. Okay, V rho G, where V is the volume immersed. Let's solve this now. Now we can see that now the density of water in kg per meter cube is 10 to the power 3 kg per meter cube, but the density of water in grams per centimeter cube is 1 gram per centimeter cube. Okay, that is one point, and you can first of all see that this G cancels out throughout. Okay, G can be cancelled out throughout, so you are left with 32 minus volume of A. This density will be 1, right? On both the side, the density of water is 1. Okay, 1 gram per centimeter cube. We want the answer in grams, so we are placing everything in CGS unit. Okay, 32 minus VA. Okay, this will be 1, and VA is volume of A. We can write volume of A as mass upon density, right? Density into volume is mass, density into volume is mass, so volume will be mass by density, which will be 32 by 8, right, 32 by 8, which will be 4, sorry. Okay, so volume will be 4 centimeter cube, right, volume will be 4 centimeter cube, so you can plug in the value over here. This will be equal to MB mass of B, which we want to find, and this will be again rho is 1, right, volume of B again we can write it in the similar fashion, mass of B divided by density of B, density of B is 5, right, so just substitute MB by 5. Now just solve for MB and you'll have your answer. This will be 28, here you'll have 5 minus 1, that will be 4 MB by 5, so 28 into 5 by 4 is equal to MB. 4 7s are 28, 7 5s are 35. 35 grams is the correct answer. Okay, I hope the approach is very clear. The only concept was apparent weight of A equals apparent weight of B, and some wise solving over here. Okay, mass is equal to density, volume is equal to mass by density. Okay. So question 14 over here, in this question you are given that two liquid drops of radius small r combine to form a bigger drop of radius capital R. Okay, you are supposed to find the surface energy of the bigger drop, it is given that the surface tension of this liquid is T. Okay, quite a simple job. What you'll write, the surface energy of the bigger drop is equal to tension into area, right? Surface tension into area. So area of that bigger drop will be 4 pi capital R square. That's it. If you see, the answers over here are given in terms of small r square. So what we need to do, we need to express this r in terms of small r. Okay, express this r in terms of small r. And how we are going to do this? We are going to say the initial volume is equal to final volume. Okay, we are going to conserve volume. Okay, so the initial volume is equal to final volume. This two combined, this two liquid drop just combined to form this one, right? So initial volume is equal to final volume. So I can write the volume of this as 2 into, I'll just multiply this by 2. So 2 into 4 upon 3 pi r cube, right? 2 into 4 upon 3 pi small r cube is equal to the volume of this one. It will be 4 upon 3 pi r capital R cube, right? So 4 upon 3 pi will get cancelled, and you'll get 2 small r cube is equal to capital R cube. Okay, take cube root on both the sides. So 2 to the power 1 by 3 is equal to r, 2 to the power 1 by 3 into r into small r is equal to capital R. Okay, so you expressed r in terms of small r. Okay, so that job is done. So just substitute over here 4 pi and r square. Now you want r square, so square it. So you will get 2 to the power 2 by 3, just squaring it, right? So yeah, so squared it. So 2 to the power 2 by 3 and r square. Okay, now if you match the options, you can't see any. So but don't give up when you're closest. Okay, the answer is just in front of you. All you need to do is express this 4 as 2 to the power 2. Okay, so that is what you need to do. So 2 to the power 2 into 2 to the power 2 by 3, and then you'll have the other terms T pi r square. Okay, so this will be 2 plus 2 by 3, right? Same base, so the powers will add. So 6 plus 2, 8, 8 by 3. So 2 to the power 8 by 3 here. 2 to the power 8 by 3 pi r square into t. 2 to the power 8 by 3 pi r square by t is the correct choice. Okay, so I hope the approach is clear. Volume conservation, and just to express this r in terms of small r, and then just apply the surface energy formula, surface tension into area. Okay, over to the next question. Question 15 over here, now from the moderate category. Okay, so we have increased the level even more. So congratulations, first of all, if you made it this far. Why don't you subscribe? Anyways, so in this question you have a capillarity tube which is open at both the ends. Okay, the liquid in this capillarity tube is water, density of water is rho, surface tension is T, the radius of this capillarity is given as small r. Okay, you are supposed to find the length of this liquid column. First of all, you can't see a straightforward approach to this question, right? So that's why it is a moderate category question. So let us discuss it now. Okay, so here we have our liquid column. So we'll consider 4 regions. One region is the top end. Okay, the top end, here it is region 1. Okay, this is region 1. Region 2, okay, is just below the meniscus, just below the first meniscus. Region 3 is just above the second meniscus over here, and region 4 is to the other end. Okay, now we'll find the pressure at each of these points, and then we'll have our answer. Okay, magically we'll have our answer. So at P1 the pressure will be nothing but atmospheric pressure, right? It's open at both ends. So at P1 the pressure is nothing but P0. Okay, let's consider the atmospheric pressure as P0. Okay, now the pressure at 2, what will be the pressure at 2? Now I mentioned this in the earlier questions that pressure at the concave surface is slightly more, right? And the pressure at the other surface is less by 2t minus r. Okay, so this P2 will be P1. P1 is nothing less but P0, right? So let's directly write it as P2 is equal to P0 minus 2t by r. Now this r is the radius of your meniscus. Okay, anyways, in this case r is equal to r. Radius of the capillarity is equal to the radius of your radius of capillarity equals radius of meniscus. Why? Because it is water. Angle of contact the angle of contact is 0. Okay, we can consider it as almost 0, although you can see a concave surface over there. It makes an acute angle, I know, but you can consider the angle of contact approximately to be 0. Okay, so it's a fair assumption that r is equal to r in this case. Okay, so in place of r, the radius of meniscus, I'll just substitute the radius of capillarity. Now pressure at 3 will be nothing but pressure at 2 plus the pressure due to the liquid column, right? So pressure at 3, okay, pressure at 3 is equal to pressure at 2. Okay, I can directly write it this way: P naught minus 2T by small r, okay, P naught minus 2T by r, plus pressure due to the liquid column, which will be nothing but rho gh, right? Rho gh. So rho g, and the depth over here is L. Okay, now pressure at 4, you can see that 4 is again exposed to atmosphere, right? So here we can write pressure at 4 equals P3 minus 2T by r. In first place, we can write, first of all, we can write pressure at 4 equals P naught, right? Because it is exposed to atmosphere. And in second way, we can write C. This is the concave surface, right? 3 is in the concave surface. Now this is the other surface. The pressure in the other surface will be P3 minus 2T by r, just the similar case. Okay, so it will be P3 minus 2T by r, whatever the pressure is in the concave surface, minus 2T by r, similar to this, right? Whatever the pressure is in the concave surface, P naught minus 2T by r. Okay, that will be the pressure in the other surface. Okay, so P3 minus 2T by r, that is the pressure in the fourth surface. Now substitute P3 over here, you can see that it will be P naught plus minus 2T by r plus rho gl minus 2T by r. Okay, so you can see that P4 is equal to P naught. Okay, I can remove this intermediate step now. Okay, I hope that is clear. I just substituted the value of P3. Okay, P3. Yeah. So I'll remove this intermediate step now. So we can write P4 is equal to P naught is equal to this. Okay, so this and this can get cancelled, and you will see that rho gl is equal to rho gl minus 4T by r is equal to 0, which means that rho gl is equal to 4T by r, and L is equal to 4T by r rho g. This is the correct option. Okay, so that will be option A, right? L equals 4T by r rho g. I'll just sum up the procedure, the approach. Okay, so first we made 4 regions over here: region 1, region 2, region 3, region 4. So region 1, the pressure is P naught. Region 2, it's the other surface to concave surface, which means the pressure will be P naught minus 2T by r. Okay, r is equal to r. I hope you got that idea. For water, the angle of contact is almost 0. Okay, for P3, the pressure will be P2 plus rho gl, right? P2 plus rho gl, we substituted the value of P2. Now for P4, again it is exposed to atmosphere, open at both the ends, so it's P naught, and then we found out the pressure using other way, P3 minus 2T by r, P3 minus 2T by r. So P3 we substituted over here, P3, okay, P3 minus 2T by r, okay, and then we found out that P naught and P naught will get cancelled, and finally we'll get the value of L as 4T by r rho g. I hope the approach is clear. You can note this down. This is a very good question. The notes will be available on website too. Over to the next question now. So question 16 over here, this is the last question for the day, and then I'll give you your homework question, and then we'll wrap up with the class. Okay, so here in this question you are given a capillarity tube. The top end of this capillarity tube is 2 centimeters above this water level. Okay, this liquid is water. Surface tension of water is 0.07. The radius of this capillarity is 0.25. Okay, 0.25 millimeters. You are supposed to find the angle of contact at the top end of your capillarity tube. Okay, so first of all, will the angle of contact change? Angle of contact of water change? Okay, the obvious answer will be no, right? Angle of contact won't change. So just in the previous question we discussed that the angle of contact of water, we can approximate it to 0. So the angle of contact in this case should be 0, which is not there in the options. Okay, so what is happening over here? So let's say it. First of all, find H. Okay, what is the rise in the liquid level in the capillarity tube? Okay, so let's find H by considering that the angle of contact is 0. Okay, so 2t cos theta upon r rho g. This is the formula, right? So 2 into t, so 2 into 0.07 into cos theta. Cos 0 is 1. Okay, theta is 0, right? We assume that angle of contact of water is 0. So cos 0 is 1. R is 0.25 millimeter. So let's convert that into meters into 10 to the power minus 3. Rho, density of water. Density of water is 10 to the power 3 kg per meter cube. Okay, in CGS it's 1. Okay, and g, what is acceleration due to gravity? Let's consider it as 10. So this and this will get cancelled. We'll get 2 into 7 into 10 to the power minus 2. 25 into 10 to the power minus 2. This and this can get cancelled and divided by 10. Okay, so here you can see 14 divided by 250, right? 14 divided by 250. I hope the calculation is correct. Okay, so let's solve it. So 14 divided by 250, or I can say 14 divided by 25. 14 divided by 25, I'll keep this 10 aside. So 14 by 25, I'll multiply it by 4, so that will give me 56 by 100, right? Some maths tricks over here. So you can shift the decimal. So you can see this is 10 to the power minus 3. You can write 56 into 10 to the power minus 3. Okay, so this is the height, right? So I just took it to the denominator. So 56 into 10 to the power minus 3. I hope that is clear. Now I'll convert it in centimeters. This is in meters, right? So I'll write 5.6 into 10 to the power minus 2. Okay, and this is in meters. So 5.10 to the power 2 meter is nothing but 1 centimeter, right? So 5.6 centimeter. Height is 5.6 centimeter. Height is 5.6 centimeter. But the height that we have over here, the available height is just 2 centimeters. Okay, so that is the thing happening over here. This is a particular question of your capillarity of insufficient height. Okay, where the height of the liquid rise is more than the height of the capillarity. Okay, so here in this case, what will happen? There will be a fountain. No, there won't be any fountain as such. What will happen is that this water will rise up and change its angle. Okay, it will change its angle in order to see if it changes its angle. Okay, 2t cos theta by r rho g. Everything else will remain same. T, tension will remain same. The radius of your capillarity will remain same. Your density of water remains same. Acceleration due to gravity of course remains same. So what will happen is that this water will flow up and change its angle. It will increase this theta. Okay. Initially it was 0, right? We considered it 0 and found the height to be 5.6, which can't be the case, right? We want the height to be 2 centimeters. The maximum height that we can allow is 2 centimeters. Okay, so now what will happen? It will go to the top and it will change its angle. So it will increase this theta. It will increase theta. Cos theta will decrease. Okay, cos theta is decreasing function. If you increase theta, cos theta will decrease. If you see cos 0 is 1 and cos 90 is 0, right? So if you increase theta, cos theta will decrease. So what it's doing, the water is going up, it's changing its angle. So here you can see a hint over there. Okay, angle of contact at the top end. Okay, so it's changing its angle at the top end. So at the top end, the angle is increased. If the angle increases, cos theta decreases and hence the height decreases. Okay, so now our job is to find that angle. Okay, I hope the approach is clear. You can note this down. Just ignore the dogs. Okay, I'll clean this up and then we can find the angle. Now time to find the angle, so we'll write it as cos. Now again write the height formula, okay? But now keep in mind that the maximum height that we can allow is 2 centimeters, right? The liquid cannot rise above 2 centimeters, okay? It is going to change angle then, okay? So H equals, again let's write 2t cos theta dash now. The angle has changed, height has also changed, it will be 2 centimeters now, okay? And divided by r rho g, all of this remains constant. So you can see that cos theta dash will be equal to r rho g into h dash divided by 2t, right? Cos theta dash is equal to r rho g into h dash divided by 2t. Now substitute these values. R rho g, r is this thing 0.25, so 25 into 10 to the power minus 2, and millimeters, so 10 to the power minus 2 into 10 to the power minus 3, that is 10 to the power minus 5. Rho is 10 to the power 3, okay, and g is 10. H is the maximum height that we can afford is 2 centimeters, so 2 into 10 to the power minus 2, okay, divided by 2 into t, divided by 2 into 0.07, okay. Now this is a bit calculative, so 25 into 2, that will be 50, or you can cancel this 2, right? So you can cancel that and you'll be left with 25 into some powers of 10, 10 to the power, this will be 10 to the power 4, and 10 to the power minus 1, 10 to the power minus 3, okay, that will be 10 to the power minus 3, okay. This is 10 to the power 4, 10 to the power minus 1, and 10 to the power minus 3, okay. And here you'll get 7 into 10 to the power minus 2, this and this will get cancelled, and you'll be left with 10 to the power minus 1, okay. So 2.5 or 25 divided by 7 into 10 to the power minus 1, okay. So 7 over here, 25 over here, 7 3s are 21, so 0.7, 7 5s are 35, okay. So let's leave it over here, 3.5. So we get 3.5 into 10 to the power minus 1, which is 0.35. Now we want theta, so we have to find inverse of that. So how will we do that? Easy job. Look at the options, okay. So of course it can't be 90, right? Cos 90 is 0, right? If this angle theta dash was 90, this value should have been 0. We found that cos theta dash is equal to 0.35, okay. It can be 70, let's see. If you know that cos 60, now one thing we know about cos is a decreasing function, right? So as the value of theta increase, cos theta will decrease, okay. So you just have to apply a lot of logic over here. So here we know that cos 60 is half, right? Sin 30 half, cos 60 half. So we know that cos 60 is half is 0.5. We want the value to be 0.35, okay. This is less, right? 0.35 is less than 0.5. So we want to increase the angle, right? We want to increase the angle more than 60, so that the value of cos theta becomes even less, okay, less than 0.5. And so the only option left with us is option B, which is 70. 90 cannot be option. We want an option which is greater than 60, and the only option is 70, right? Okay. I hope the whole idea is clear. This was a question from a capillarity of insufficient height, okay. If you would like to practice more questions of such type, you can, I'll try to put some on the website, okay. Anyways, let's wrap up with today's class. I'll give you your homework question now. You can note this question as well, okay. So yeah. So question 17 over here, this is your homework question. You can pause and take a screenshot if you wish to try it later. You can pause now and take a screenshot, okay. So that's all for today's class. I hope you enjoyed it. If you did enjoy it, smash like, subscribe. I'll see you soon in the next class of A series, probably with a bunch of new markers, okay. So keep enjoying physics.